This is a Branson L20 ultrasonic welder. General Motors uses ultrasonic welding for the manufacturing of face masks and battery tabs. Ultrasonic welding is a process that uses mechanical vibrations to generate friction between two workpieces, creating weld seams. Ultrasonic welding is advantageous because it is cleaner and more energy efficient than alternative welding methods. Currently, there are no solutions to effectively determine an ultrasonic weld head failure. General Motors has tasked our team with detecting weld head failures by developing a solution that can detect and measure the frequency and amplitude of vibration of an ultrasonic weld head. This is because deviations in the frequency and amplitude of vibration indicate system failure.
So how do we measure the frequency of something that oscillates 50 times faster than the flap of a bee's wings and at an amplitude of half a hair's width? With this being the case, we had to come up with some creative solutions.
Our team's goal was to design a hardware and software solution that converts the mechanical motion of the weld head into an electrical signal we can process. Our system must have a fast sampling rate, high resolution, incredible accuracy, instant processing time, and would be within a $300 budget.
Our process for designing a solution was to, first, identify the problem, brainstorm and research potential solutions, use a design matrix to choose a solution, model that solution, perform iterative testing on that solution, then evaluate our results. Using this engineering design process, we were able to narrow down to two solutions.
The first solution we developed was a grounding probe sensor that uses a microcontroller to measure frequency through physical contact. The grounding probe works as a quick-acting switch that shorts a circuit when the weld head makes contact with the probe. To test our solution at lower frequencies, we created a hammer machine that works like our grounding probe. When the hammer makes contact with the grounding plate, it shorts the circuit and generates a square wave signal that allows us to convert the mechanical movement into an electrical signal. From this signal, the microcontroller can then determine the frequency. To further test our concept, we used a function generator to force a speaker to oscillate at higher frequencies and measured them using our grounding probe sensor. After simulating our sensor, we constructed a grounding probe to be fitted on an ultrasonic welder. To dampen the impact of the weld head, we attached a spring to the end of the probe. Finally, we mounted our probe using an articulating arm with a magnetic base that was attached to the welder's anvil.
The second solution our team developed utilizes concepts in optics to magnify the travel of the weld head. To do so, we reflected a laser at a predetermined angle of incidence onto a mirror attached to the tip of a weld head. The reflected laser is projected on a photodetector, which operates by producing a power signal based on the position of the laser on its face. Our team then generated a math model to relate the displacement of the weld head to the movement of the laser across the photodetector. With this math model, we were able to create a transfer function that determines the frequency and the amplitude of the weld head based on the power signal from the photodetector. For our final prototype, we constructed an adjustable and modular platform to house all of the electrical components. The platform keeps the laser and the photodetector at a known distance apart, and the rotating bezel allows us to change the laser's angle of reflection. As for the results, using the grounding probe, we were able to detect a 20 kHz frequency of the weld head. And with the laser, we can make some improvements to the mounting to make this a more viable solution. Using these prototypes, we can help manufacturers predict weld head failures, which we can improve their quality control, saving them time and money. This Capstone project allowed us to experience a real-world engineering problem and helped us understand the engineering design process. It also helped us with our team building, and it allowed us to see a project from start to finish. Thanks for watching, and we hope you've learned something.